session on finite element analysis. In this session, we are going to discuss about shape function and its importance in FEA. Shape functions play a crucial role in the finite element analysis method, which is a numerical technique used for solving complex engineering problems. FEA involves dividing a complex structure into small, simple elements, connecting them at nodes, and then applying mathematical models to analyze the behavior of the entire structure. Shape functions are essential components in this process. Here is why they are important. Interpolation of field variables. In FEA, physical properties such as displacement, stress, and strain are typically interpolated within each element based on known values at the nodes. Shape functions are used to interpolate these field variables across the element, providing a continuous distribution of values within the element. So we can use shape function to find the value of these field variables at the nodes that we desire, and also interpolate and find the values between the two geometrical nodes. Representation of element geometry. Shape functions define the geometric shape of an element. Different type of elements, example linear, quadratic, cubic, have different sets of shape functions that represent their geometric characteristics. The choice of shape functions influences the accuracy of the analysis. I'll show you some 1D and 2D linear, quadratic, and cubic elements. You can see here, this is the first one. When I say linear for 1D element, it means two nodes, and this center part is the element. When we say quadratic, there are three nodes and two elements. When we say it is cubic, it means there are three elements and four nodes. When we talk about 2D element, there are three nodes and there are three elements in between. This is also called as CST element, that is constant strain triangle. Then we can have six nodes, as you can see here. Now there are six elements, as you can see, 1, 2, 3, 4, 5, 6. This is called as LST element, that is linear strain triangle element. For LST element, there are 6 nodes and 12 displacement degrees of freedom, which means at each node there will be 2 degrees of freedom. In CST element, there are total 6 degrees of freedom. At each node there will be 2. And the third one, wherein the nodes is 10 and there are 9 elements, as you can see. And there is also one node at the center. QST element means quadratic strain triangle element. It is also called as cubic displacement triangle, hence the name cubic. So that is how you represent the elements, and this is a shape function which is representing the element. So when I say the shape function for CST element, it would indicate that you are representing with the help of CST element. When you talk about LST element and you can write the particular shape function, you would indicate this shape of the element. Mapping from physical to natural coordinates. Elements in FEA are often defined in natural coordinates, which are local coordinates within the element. Shape functions map the physical coordinates, which means the x and y. That is the general way of writing of a point within the element to its natural coordinates zeta, eta. These two are the natural coordinates, facilitating the application of numerical integration techniques. So you will be able to solve the problems easier when you convert them into natural coordinates as compared to physical coordinates. You can go through the FEA lectures which I have created, wherein you will understand the change of coordinate system from physical to natural. Derivation of element stiffness matrix. The stiffness matrix for each element is a fundamental component in FEA, representing the element's response to applied loads. Shape functions are used in the derivation of the stiffness matrix, which relates nodal displacements to nodal forces within an element. So this is another application of shape function in the derivation of stiffness matrix itself. Assembly of global system equations. Shape functions play a role in assembling the global system equations by relating the nodal displacement and forces of individual elements to the overall behavior of the entire structure. So shape function basically helps you relate the displacement and forces, but it is not about a single element. It will be about all the elements together which forms the global matrix. This is crucial for solving the system of equations that represents the entire structure. Treatment of boundary conditions. Shape functions are employed in enforcing boundary conditions at the nodes of the finite element mesh. They help in accurately applying constraints and loads, ensuring realistic simulation results. So this is another place where you can apply shape function for allocating proper boundary conditions at particular nodes. Say if there is a load or there is fixed, so accordingly you can use it. Adaptability to different element types. FEA allows the use of different element types, example truss, beam, shell, solid, to model different aspects of a structure. Shape functions are specific to each element type, enabling the method to be versatile and applicable to a wide range of engineering problems. So these are the various types of elements which are possible in FEA. Like suppose if you have a solid element or you have a shell element, beam element, rigid elements, membrane elements, infinite elements, spring and dashpot, truss element. So in all these cases, the shape function will be different so that you are able to define them with respect to their element shapes. So let's lastly talk about the key points of this session. In summary, shape functions are foundational in FEA as they enable the representation of physical quantities within elements, facilitate the mapping of coordinates, aid in the derivation of element stiffness matrices, and contribute to the overall accuracy and efficiency of the analysis. That is all we have discussed in all the slides above. The appropriate choice and accurate implementation of shape functions are critical for obtaining reliable and meaningful results in FEA simulations. So it is very important to define the shape functions properly so that we are able to get better results. Also, it will help you reduce the error and converge towards a better solution. So with this, I end the session. I hope you have understood the session. If you have any doubts, please write to me in the comment section. Don't forget to like, share, and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.